So factor analysis and reliability analysis. So factor analysis is a technique that allows the recombination of independent variables. It's typically used by those who specialize in polling when they want to recombine variables to increase the accuracy of predictions in a model. Generally in international relations, the field I come from, we don't use factor analysis because it takes variables that are coherent and understandable, disintegrates them, recombines them according to a principle of maximizing their ability to make predictions, but you lose all ability to describe these in a tangible way. So it becomes a problem of understanding and then communicating this understanding of this new variable. If your goal is to predict and not have to explain how the prediction was procured, then it's a technique that works. So we're going to apply it here because we saw that there were instances of multicollinearity where we had variables that were multicollinear, exceeding 0.75 in correlations with each other, and this is a violation of the diagnostics of ordinary least squares. So you could apply factor analysis if you have a strong theoretical reason to exclude neither variable. So SPSS will generate multidimensional indicators for you through a procedure known as factor analysis. This is useful when you have 20 or so independent variables, which is too many for an unbiased assertion into a linear regression. And so you use factor analysis to merge those 20 variables into 4, 3, 2, or even 1 independent variable. Although, of course, it makes conceptual interpretation difficult. Factor analysis can also be used to merge variables together that otherwise indicate multicollinearity. These new separate factors, which is what they're called when you've got these new combinations of variables, are created in a fashion that reduces their bivariate correlations, significantly reducing multicollinearity. This can be examined by applying a bivariate correlation. In other words, once you've produced these new factors, which are really new variables, by disintegrating the previous variables, these variables should not be easily correlated with each other, because the principle of factor analysis is that it breaks up the variables into components that are correlated and puts the components that are not correlated into separate factors. So basically, factor analysis takes different parts of different variables and groups them according to how they affect a dependent variable. So it can take 3 old variables and make, for example, 3 new variables, each of which is made up of parts of the first 3 old variables. The use of too many IVs will artificially inflate the R squared. So factor analysis can be used to squeeze 10 variables into a number of variables or factors desired, typically 3. It can be used to test whether certain facts are associated with each other as well. Now, it's very important that factor analysis be driven by theory. Otherwise, you're going to lose the logic for which they were constructed. So we're going to retrieve the data set, SPSS China save. All right, here it opens up. Now we want to combine the independent variables of rat herb, which is the ratio of urban populations between China and its main competitors, rat total pop, which is the ratio of the total populations of China and its competitors, and rat energy, which is the ratio of China and in energy with its main competitors. And we're going to try to combine these into a single common measure of power. In other words, into a single variable or into a single factor. So here's the procedure for that. We go to Analyze, Dimension Reduction, Factor. And here we're going to insert rat herb. Here's rat total population, rat energy, and rat herb. So these are the 3 independent variables. So we now go to descriptives, and here we're going to select KMO and Bartlett's test of sphericity. And we click continue, and then we go to extraction. And we go here to the method on top, and we select principal components, which is the most common method by which you have the factors disintegrated. Then we go to the display, and in display we select Scree plot, which is going to be a graphic. And then in extract, if we want to optimize the selection of factors, then we select extract based on eigenvalues, and then we click continue. If you want to choose how many factors are produced, then you would select fixed number of factors. So here eigenvalues will determine how many factors, but will typically result in one. If you want to have more than one variable, you would put it here under fixed number of factors. Normally, you would indicate 3. What we want to do is create a single combined factor, so we're going to leave it by allowing the eigenvalue to determine the number of factors. Okay, then we click continue. Then we select rotation. And here we select none, which is the default method, or Verimax, which is very commonly used. So I'm going to leave it at none as the rotation method. But most of the publications I've seen have used the Verimax method. And then we click on continue. And then we click on scores. And here we want to say save as variables, because we want to save the result as a variable that we can then insert into a subsequent model. All right, we click continue, and then we click OK. All right, now the first thing you're going to notice when we go to the data set is that we've created a new variable, FAC1 underscore 1. Underscore 1 indicates which version of that particular variable. If we recreate the variable twice, it'll be FAC1 underscore 2. So let's interpret the output that we've produced. So step 1 here, we have KMO and Bartlett's test. These both test the multivariate normality and sampling adequacy for factor analysis. The KMO, which is the Kaiser-Meyer-Olkin test, measures if the distribution of values is good enough for factor analysis. A score of less than 0.5. Here we have a score of 0.717, but a score of less than 0.5 suggests that the data is poorly distributed for factor analysis. So this is a significance test, the KMO test and the Bartlett's test. So the interpretation of Bartlett's test of sphericity, which is the next 3 lines below the KMO test. The Bartlett test of sphericity measures the multivariate normality of the data distribution and also tests if the data correlation matrix is an identity matrix. You guys might recall the linear algebra that we did to solve for multivariate linear regression, where you've got a matrix in which you've got zeros and ones, and the ones are diagonal. That's an identity matrix. So here we've got linear algebra. A significance test of p less than 0.5 indicates that there's a low probability that the correlation matrix can be rendered into an identity matrix. Okay, here we have a significance of 0.000. That, which actually indicates that there's a low probability that the correlation can be rendered. So here this is not a positive test. We have a failure on the Bartlett's test of sphericity, but a pass on the KMO test. All right, now we go on to the interpretation of the commonalities. It indicates how much of each original independent variable is included in the new variable created by factor analysis. And here you can see it basically comes out to proportions. Right, you got 87%, 87%, and then 75%. So some parts of the variable are discarded. And so when there are multiple factors created by factor analysis, it indicates what portion of each original independent variable is associated with which new factor. Recall that factor analysis disintegrates old variables and then redistributes them into the new factors. This is one of the reasons why it's so difficult to interpret, even if it does reduce multicollinearity and allow these concentrated parts of variables to be put into these new factors. These new factors are then very difficult to interpret. You might have some variables in which seasonality is present in all of the independent variables, and so those are somehow grouped together. And if the seasonality is common, then it makes sense to do it. So the interpretation of the Scree plot. Here we have the Scree plot, which is a graph, and you can see the component number at the bottom, 1, 2, and 3. And you've got the eigenvalue, which was used to determine at what point optimally how many of these new factors should be created. The Scree plot is used to help identify the number of factors that should be selected. Now, what's the optimal number of factors? The point at which the eigenvalue and the component number intersection stops being very steep indicates the typically chosen number of factors. The Scree plot here indicates that 3 independent variables would have been more optimally combined into 2 factors rather than the one that we forced here. So if you see the component number at 2, you've got the sort of ski slope that comes down. And number 2 is what we should have chosen for the number of factors for the model. So here we've got the, finally at the very bottom, the interpretation of the component matrix. These results indicate that certain variables are in fact more interconnected than others. And if there is more than one factor, it indicates which original independent variables and how much are associated with which new factor. And so it's interesting. Here we've only got one component. But if we had 3 independent variables, we'd have 3 components, and you could see how much of each variable is combined into those. So this is factor analysis. I would recommend that it be used very sparingly. It might be able to solve a problem of multicollinearity, but that's only if it's appropriate to combine the set number of variables into a set number of factors. It may not be optimal. If you do the recombination and you were to run a Pearson correlation test, a test for multicollinearity, you should find that these new factors, these new variables that you've created, are not correlated. So let's go on and conduct a reliability analysis. Now, it's important with multidimensional indicators, including factor analyses, factors, to test how reliable is each respective measure. So once the face and construct validity of a concept has been theoretically established, the reliability of the measure, that it will measure what is intended to measure in all the succeeding tests, can be established by reliability analysis. So when we say a face validity, what we mean to say is the basic concept logical? Is the data source that we're using for the concept measuring what we think we're going to measure? And this is very important because it's very difficult in statistics to measure directly what you're trying to measure. So we use tangential measures to try to get at the underlying concept, especially in political science when we're thinking about things like legitimacy. How on earth do you measure legitimacy when people themselves are not consciously aware of what is legitimate or not? Because they may not have experienced illegitimacy, and so they have no ability to contrast it. So, that's political science, measuring things that are not always tangible. And construct validity means how do we combine it? Does the math make sense in the way that we create these multidimensional indicators? So the Cronbach's alpha measures whether there is a consistency by examining the mean scores of all pairs of tests, and a score of less than 0.5 indicates an absence of reliability in the measures. Cronbach's alpha coefficients are very similar to basic measures of association in that they range from a low of 0, indicating a low level of reliability, to a high of 1, meaning perfect reliability. So to calculate the reliability of combining the 3 original independent variables, rat herb, rat total pop, rat energy, we proceed as follows. We go to analyze, we go to scale, we go to reliability analysis. And here we're going to drop in the same 3 variables we did before, which is rat energy, rat total pop, and rat herb. So all 3 variables are now inserted. We go to statistics, and we go to descriptives on the top left. And here we're going to click on scale if item selected. And then we're going to select at the very bottom Hotelling's square and Tukey's test of additivity. Okay, and then we click continue, and then we click OK. And this is going to give us some new values. Right, so I'm just going to put it into perspective here. So let's interpret some of these components. Right off, we want to look at the interpretation of scale if item deleted, which is here in the second chart, scale mean if item deleted. This statistic permits examining whether the removal of a given variable will improve the Cronbach's alpha. If it does, then that variable should be removed as it weakens the reliability of the overall aggregate of the variables or the factors. Variables can be excluded until there's no variable removal that will improve the Cronbach's alpha value. So here you can see Cronbach's alpha if the item is deleted. So if you get rid of rat herb, it seems to improve the Cronbach's alpha to 0.796. Negative values of the Cronbach's alpha are generally indicators that the components of the original independent variables do not covary. Remember, you want the independent variables not to covary so that you don't have multicollinearity, but if you disintegrate them and recombine them, you want the new components from the different variables concentrated in the new factor to then not have a correlation or multicollinearity with other independent variables. A negative value indicates that recombination is not appropriate. It's not going to reduce your correlation between these new factors. So right away we can see that removing rat herb is going to improve Cronbach's alpha. Removing rat energy and rat total pop is not. So interpretation of the chart at the very bottom, Hotelling's t-square. Hotelling's t-square is a multivariate t-test that tests whether all of the means of the variables are equal. All right, and you can see here the significance is high. The Tukey's test of additivity, which you can see here, tests for linear dependency between the entered variables. So these are all testing for collinearity, which again it comes out of linear algebra. Both of these tests can be evaluated by their F-test significance, which is the specific test being conducted here. And you can see both significance tests are very low, 0.000, which indicates there's almost no likelihood of a false positive, which means the relationship we're seeing is real and therefore the tests are valid. So now we're going to interpret the Cronbach's alpha, which is at the very top here. So as a general rule, we usually like to work with multidimensional measures that have a reliability coefficient of at least 0.5. All right, so we have that. Right, we have at least 0.5. The Cronbach's alpha varies in value from 0 to 1, and higher values indicate better reliability. So we have a minus 0.823. Negative values, however, indicate that components of the original independent variable do not covary. This tells us we should never have combined those three independent variables into one. These three independent variables are not suited, therefore, to being combined through factor analysis into one. And we knew this from the Scree plot in the multidimensional test for factor analysis, that we should have combined these into two factors and not one single factor.